and kind of get that straightened out because that's the introduction. So trigonometry always revolves around angles. Some of this would be real simple, straightforward review to you. It depends on how much trigonometry or pre-calc you've had in the past. So there's basic definitions you want to make sure that you review. So if you have an acute angle, that's just an angle that's less than 90 degrees, and it's strictly less than 90 degrees, and it's really bigger. So it's really between 0, the angle, and then 90 degrees like that. So it's strictly less than. So something like 46 degrees, okay? A right angle is exactly 90 degrees. So in trigonometry, you work a lot with right angles because there's a part of trigonometry we call right triangle trigonometry. Obtuse angles are greater than 90 and less than 90. Again, if you want to write this in interval notation, you would say parenthesis 90 degrees, comma 180 degrees there, because it doesn't include those two endpoints. So an example would be 130, and then a straight angle would be just 180 degrees, okay, like that. So that's stuff that you learn, I don't know when you learn that, in elementary school, I guess, okay? So it's basically, since you're talking about angles, you want to review that terminology, okay? Now, what we're going to get into talking about here is angles and standard position and, some little twists that you're going to do on this. First of all, most of the time we're going to look at angles that are in standard position. So in trigonometry, what we mean by standard position is this vertex where the angle comes together. That's always at the origin. It's not out in space somewhere. And then the first side is going to be on the x-axis. One thing that you want to label on there, because this is not on that diagram, where you start is called the initial side. I would label that because that's vocabulary you want to know. And where the angle ends is called the terminal side. Okay, so what we're going to do is we're going to sketch angles, okay? So we're going to start off pretty simple on here. So, and then we'll kind of get to some of the other kind of things you'll see in trigonometry. So if you're sketching 120 degrees and you want to do this in standard position, first thing you always want to do is just highlight the x-axis. Okay, that's your initial side. Okay, that's how you do that. Now your terminal side, and this is just from your background, students usually are on top of this, that's 0 degrees, 90 degrees, right? 180, what's that? 270, and then 360. So all the way around the circle's 360. So we're going to focus on that just for a few minutes. Now you estimate. You don't have to get a protractor out, okay? Did you ever learn how to use a protractor in 3rd or 4th grade or whenever? Okay, we're not going to use protractors, you're just going to estimate. So what you do is just kind of estimate. 120 degrees is over there somewhere. That's not a very good estimate because it's really a little bit more like this. So if you think about this, if that's 90 degrees, then you would go 30 degrees more, okay? And then the other thing that you're going to learn to do on this is you're measuring this counterclockwise. We're going to talk about negative angles and positive angles tonight. So you want to show that angle is going in that direction. That's also a requirement for what you're doing there. So that's how you would draw that in standard position, okay? Right? The next thing we want to do is 340 degrees. So again, always label that x-axis. That's important that you don't forget that because I got to know where you're starting and where you end. Okay, just kind of think about where it goes. That would be 90, 180, 270, 340 is almost all the way around, okay? How much further do I have to go? 20 degrees, right? Okay, so you got to go 340 and 20 degrees more, so you kind of use that as an estimation. See, that little angle in there is 20 degrees, and then what you want to do is show that you're going counterclockwise. So use that arrow like that, okay? So that's the standard starting point of this. We're almost always going to do our angles in standard position. So start at the x-axis, terminate in one of the quadrants, and then show that you're going counterclockwise, okay? Okay, now, if usually students never learn anything about angles being bigger than 360 until you're in a trig class. Okay, it's kind of like your teacher tells you 360, that's it. Okay, well, that's not it. They're infinite. They can get infinitely big. So the idea is you can have angles that are larger than 360. All that means is you're going an extra lap around the circle. So this would be an example of a 405 degree angle. The idea would be if you take 405 and subtract 360 from it, you'd be left over with 45, right? So what you do on this is you show this like this. You would start at this initial side, and then you would show that's one lap, and then I terminate there. So that's actually how you would draw the graph of a 405-degree angle. You have to again show that it's counterclockwise, show where it starts and show where it ends. Okay? So angles can get infinitely big. There's a reason for that. It's because of physics. Okay? We have lots of applications where angles need to get bigger than 360. One of the best examples is when you drive your car. Every time a minute goes by, your car's engine cranks out way more than one time. Okay, that's what your tachometer does. It may be going through 2,000 revolutions in a minute. So that angle is 2,000 times 360. You see what I mean? Okay, and then when you're looking at things called velocity, angular velocity, it has to be bigger than that. Okay, so that's the kind of the motivation behind that. Negative values, you can also have negative angles. So negative angles just mean that you're going this way. You're going clockwise. Okay, so if you're going to graph a negative 220-degree angle, well, what you would do is you would start there, and then you would count it out. Say this would be negative 90, negative 180, and then you would terminate at negative 20. So negative angles just mean you're changing direction. Okay, and the motivation behind that's the same as the motivation for negative numbers. Okay, a little later on we began to see, well, we can, negative angles are kind of useful. Okay, so here's a couple of basic things. An angle measured clockwise is negative. So anytime you're measuring an angle clockwise, you're negative. And then if you measure it counterclockwise, then you're positive. Okay, like that. And again, angles can be negative. They can be as small or as big as possible. They can have decimals, any real number. Okay. All right, so what we're going to do, again, is we're going to work a little bit here at the beginning, just sketch out angles. Okay, you got to get totally solid with how angles work. Okay, so again, we're going to do all of these in standard position. So you want to highlight your x-axis. Okay, which way do I go on this? Counterclockwise or clockwise? Counterclockwise. Okay, is it more than one lap of the circle? Yeah, because it's bigger than 360. So what you'd want to do is you would want to do 720 minus 360, and that gives you 360 left over. So what it really means is you would be going one full lap counterclockwise, then a second full lap counterclockwise. So it's actually just like a straight angle. So you're basically, the initial side and terminal side are in the same place. Does that make sense? Okay, so it's just 2 laps around the circle is 720. That's how that goes. Okay, all right, the next one is now a negative angle. So again, if I want this in standard position, what you need to do is just highlight the x-axis. And which way does this go? Clockwise or counterclockwise? Clockwise, right? Just kind of count it out. You've got, that would be negative 90 if you made it there. If you made it halfway around the circle, that's negative 180. This would be negative 270. So you would end up being 30 degrees past that 270, but then you would be clockwise since it's a negative angle like that. Okay? All right, everybody okay with what I've done so far? Okay. How many people have had trigonometry before? Almost everybody? Is Trig new to anybody? Okay, that's helpful. Because I'm in pre-calc, if you never had Trig before, it just goes so fast, it's pretty hard. So you're kind of hoping it's more of a review. So let's see. Let me get my calculator up here real quick. So I accidentally closed it. So I want to show you a couple of things on these angles. You can use your calculator to kind of assist understanding where this angle terminates. Okay, so let me show you a couple of things that you can do on this problem. Okay, first of all, what you do is you know that this is going to go counterclockwise, so you're going to go this way. But there's 2 ways to figure this out, okay? And you can use your calculator. So what you could do is you could subtract 360, and then you still have a number that's bigger than, I did that right. So I've done that, and then I could subtract 360 again, and then that will tell me I've gone through 2 laps. So basically what I'm saying is this is 1,000 really is equal to 2 laps of 360 plus the 280 left over. So I'm going to show you 2 ways to do this with a calculator. So what you would do now when you graph this out is you would have to represent that in a clockwise angle like this. So what you do is you'd shade in your initial side. And then since it's positive, you would go counterclockwise. So you'd want to go like this, okay? Just start with 1 lap, 2 laps, and then you got to go 280 more. So count it out. That would be 90, 180, 270. So you're like 10 degrees further like that. Okay, so that's one way to do that. Okay, I like to show you 2 ways to do this, because what if you had a 10,000 degree angle? Now, I would never ask you to plot a 10,000 degree angle. I just want you to know what it means. So instead of subtracting 360 over and over and over again, what's a good idea? Divide by 360, exactly. So you can divide by 360, and if you do this, you get 27.7. What do you think 27 means? It means you did 27 laps around the circle, right? And see, if I subtracted 27, then what's left over is that's a percentage of a circle. So if you took that 0.77 times 360, then you would get this. So this would tell you you go 27 laps around the circle and then 280 more. I won't ask you to do that. You think I'm going to grade that and make sure that you went 27 times around the circle? Probably not, okay? But to get the idea is what I want you to understand. So see, this problem right here, you could have also just done 1,000 divided by 360. That would have told you you have 2 laps around the circle. And then if you take the 0.7 times 360, that would have given you 280 left over. Okay, does that make sense to everybody? Okay, that's the simplest way to do that. Okay, this next one is also more than 1 lap around the circle. So what we want to do with this is kind of figure out how many laps first of all. Okay, now what I would do on this, I wouldn't even really worry much about the negative on this. You could add 360 to it over and over again if you wanted to. Or you could even do like this. If I added 720, if I add 720, that's 2 laps. I'll show you a couple of ways to do this though. So that's 2 laps. Okay, then if I added 360 again on this, then that would take me down to negative 200. So it looks like you would basically now have 3 laps after you do that, and then plus negative 200. So that's one way to do that, is just do that. Okay, so I'm going to just kind of do this like this. Okay, I start there. It's negative, so I go clockwise this time. So I want to go 1, 2, 3 laps. I think I've done that right. 3 complete laps. Then count it out. This is negative 90, negative 180. 20 more would give you the negative 200 like that. Okay, so you can do it like that. Just figure out how many laps you have. The other thing you could do is you could go 1280, forget the negative, divide by 360, and then notice that's going to give you have 3 laps. Then if you subtract the 3, and then multiply what's left over by 360, that'll give you the, whoops, I did the wrong thing. So it's 0.555, bunch of 5s, times 360 should give you what's left over, so that's the 200, see, okay? That's the best way to do it, is divide by 360, okay? All right, everybody okay with what I've done so far? Okay? All right, so we're going to kind of really work on the basics here at the beginning tonight here, and that's how trig starts. So the next thing is quadrants. You already know that from, college algebra and everything. So one of the things is, it turns out in trigonometry, knowing what quadrant your angle terminates in is a real big deal. So it's really important on that. So your angles between 0 and 90 is quad 1. 90 and 180 is quad 2, and so forth, okay? So just kind of to make sure that you review that, you want to know what quadrants everything's in. So where's 190? Yeah, that's quadrant 3, so that would be past 180, so that's 3. We usually use Roman numerals on that. Okay, this is a negative angle, so where would negative 340 go? It's negative, so it's clockwise, so where does it end up? Quadrant 1, right, okay, you would end up 20 degrees less than 1 lap around the circle, but it's clockwise, so you have to pay attention to that then, okay? All right, if you get something like 1600 degrees, we'll get your calculator out, okay, and just do what I just showed you. So if I go 1600, and if I divide that by 360, all that's going to do is tell you that you have 4 laps around the circle, and I would subtract that 4, and then with the 0.44, what do? You just multiply it by 360, and that will tell you that you end up at 160. So what the calculator is saying on this really is, it's really saying this. It's saying 1600 is the same as 4 times 360 plus 160. Okay, we just figured out there's 4 laps. So where is 160? What quadrant is that? That's 2. Okay, so that's how you figure that out, see. Okay, and then the next one, you could just kind of reason this out the same way. If you take 720 divided by 360, that's going to give you 2. So that just means that this happens. Okay, now this is a little different situation. So if you were plotting negative 720, it's clockwise, so you would go 2 laps, but where do you end up? You don't end up in a quadrant. So the answer to this is none. You're not in a quadrant. You have to be away from one of your axes. You have to literally be in a quadrant before you are in a quadrant. You can't be on an axis. Okay, so what we call this, you would probably want to write this down. We'll talk about this a little bit later in the class. But this is called a quadrantal angle. And what that means is it just means that that angle is on an axis. So here's some examples of quadrantal angles. 0, 90, 180, 270, 360, and forever and ever and ever, right? And then if you went negative, you'd have like negative 90, negative 180, and so forth. So those are angles that terminate on an axis, okay? They're not in a quadrant. That's why we call them quadrantal, okay? Okay, now what the next thing is that's degree measure, and then we talk about radian measure, which is real important. And a lot of times students, I think sometimes couldn't really tell me what radian measure is, so I do want to kind of give you a good understanding so you know what it means. So it turns out that the fact that we have 360 degrees in a circle, where do you think that came from? Somebody made it up. Okay, they did. It could have been anything. That's not a mathematical discovery out there. Human beings just decided, let's make 360 degrees in a circle. The thought on that is that it came from, there's 365 days in a year, but 365 is a bad number. We like 360 better. Okay, that's how the Babylonians did. They had what's called a base 60 number system, where they chopped it off to make it easier because they didn't have calculators back then. So that's kind of the theory behind where this came from, okay? So let me explain what a radian is. A radian this is a mathematical discovery, okay? This is how you should measure angles. The only time you really do degrees is if you're talking about triangles, latitude on a globe, and stuff like that. But if you're working with mathematics and if you're working with calculus and stuff like that, you want that angle to be a real number measure. Okay, so let me explain what this is. And what a radian this is the definition, and this is a mathematical definition that we came up with, and it kind of led us to some discoveries about things. So basically, 1 radian is going to be that special angle where this happens. Okay, and this diagram right here shows this pretty well. So basically, if this arc is the same as the radius, then that is 1 radian. Okay, that's what a radian is. So it's a special angle, and it doesn't matter what the size of the circle is. You can make it big, you can make it small. It's always going to be the angle where this distance is the same as that. Does that make sense? That's what a radian is. Now, if you look at that, what does that look like? Around 60 or something? Maybe kind of ish? Okay, it's got decimals and stuff, but 1 radian is going to be defined to be that then. Okay? Now, what I want to do here is I want to pull something up here that I use for another class. It'll take me a second to find this. It's an applet on here that's kind of useful when you learn this then. So let me find it real quick. It's in here somewhere. It's not the pizza guy. It's not there. It's a real good app to show this, though, and I do want to take the time to show this to you. If I can find it, that is. Maybe not. Maybe I don't have that. I thought I did. If not, I'll look it up there when I give you a break, and I'll show you, because it's kind of a good way to show you visually what we mean by radians. I don't see it in there. Shoot. I was so looking forward to that too. Okay, we'll do that later. Okay, so let me kind of show you what we come up with here in Radian Measure. So the idea that's to you that's really important is Radian Measure is a real number, degree measure is not. Okay, 360 degrees is, like I said, is a human invention. Okay, so what I want to do is I want to show you this formula. This is the formula that relates the angle, and it goes basically like this. If you're in radians, we have theta. This angle is equal to the ratio of s. This s is the arc, and we call that a subtended arc. That's worth writing down because I don't have that vocabulary written out, but the subtended arc just means that that's a part of a circle that's subtended by what we call a central angle. Central angle just means the vertex is at the origin. That's a central angle right there. Okay, so what we would have on this then is this. That's the general relation. Okay, so I want to show you something on this, and this is the way our textbook does it, which is kind of a neat way to do this. So do you guys know what the formula for a circumference of a circle is? 2 pi r, yeah, okay, 2 pi r, so we'll write that down, that's important. So the circumference of a circle is 2 pi r. Well, what happens is in this diagram that I have up here, okay, what would happen is if you went all the way around the circle, that's what S is, right? A circumference of a circle is all the way around. So what I'm going to do is I'm going to show you something that gives a very, very fundamental discovery here. So it goes like this. So if you're going like this, if you're going all the way around the circle, we know that's 360 degrees, right? Okay, but if you're going all the way around the circle, S is the circumference, right? So that is 2 pi r. So I'm just going to have you put 2 pi r there and then bring down that r like this. And what happens is you get this. So you get 360 degrees is the same thing as 2 pi radians. Okay, that's where it comes from, and that's an important discovery in mathematics because that gives you the precise connection between degrees and radians. Okay, so it just means one lap around the circle is 2 pi radians. Does that make sense? Okay, all right, so don't forget that. 2 pi radians is 360. Okay, okay, now here's a couple of two things that you absolutely need to remember because I'll never give these two things to you. The first is the one I just showed you. 2 pi radians is 360. So what is 180? It's got to be pi, right? Okay, so half of 360 is 180, half of 2 pi is pi. So these are real important things to make sure that you know. That's an important connection. So one of the first things we're going to go through is we kind of get an idea of what a radian measure is. One of the things you have to do is you have to convert back and forth between radians. And the idea is if you're going to convert from radians to degrees, you multiply by 180 over pi. If you're going to convert from degrees to radians, you multiply by pi over 180. Okay, now let me show you why that's the case. And I would write this down because you want to get an idea where this stuff come from. So what we have is pi radians is equal to 180 degrees. Now I'm going to write this down twice because I'm going to solve the equation in such a way that it'll help you remember how to convert stuff. Now you can just blindly memorize it if you forget, but you'll forget it if you don't understand it. It's my theory anyway. Okay, so what I'm going to do is I'm going to divide both sides of this equation by 180 degrees because it is an equation. And what I would end up having is I'd have 1 degree is pi over 180 radians. Like that. Okay, so here's the idea. Okay, it's real simple if you think of it this way. So if 1 degree is this, then what's 2 degrees? 2 degrees would be 2 pi over 180, right? 3 degrees would be 3 pi over 180. So to me it makes perfectly good sense that if you want to change degrees to radians, that's why you multiply by pi over 180. Okay, so that's what you're always going to do. All these things that are in degrees, you multiply by pi over 180, then the conversion's done. The other way I like to look at this is like this. So if you go back to the same equation, if I divide both sides by pi, then I get 1 radian is equal to 180 over pi. Okay, so what that means then is the same idea. If 1 radian is 180 over pi, what's 2 radians? 2 times 180 over pi. 3 radians would be 3 times 180 over pi. You see what I mean? Okay, so that's how you do your conversions. And if you forget, well, this thing right there will tell you how to do that, see, okay? So this is a fundamental thing that you'll do throughout our study of trig. So we're going to go ahead and just convert some of these things. So, and if I say leave your answer in pi, that means I want pi in the answer. Okay, so here's what you do. 120 degrees, you just multiply that by pi over 180 degrees, and then you're in radians. Okay, and then what you're doing is you're reducing fractions. So if you're doing this, you can cross out the zeros. You can do whatever you're comfortable with doing in your head is okay. So you'd have 12 pi over 18, and then you can reduce that fraction. Both of those numbers divide by 6. So you'd end up having, as your answer, you would have 2 pi over 3 radians. Okay, so 120 degrees can be written as 2 pi over 3 radians. And leave the pi alone most of the time is what we're going to do. Okay, then all these are the same. So if you have negative 225, you multiply negative 225 degrees by pi over 100 degrees radians like that. And you'll have a negative answer, of course, just means it's a clockwise angle. So you'll have negative 225 pi over 180. And then you can divide this by, this is the thing sometimes I see students, because we're so reliant on calculators today, don't reduce very good sometimes. So they both divide by 45. So if you did that and worked that out with the assistance of your calculator, if you had to, that would end up being negative 5 pi over 4 like that. Okay, now I want to remind you of something on your calculator too, because I would like you to know obviously how to reduce fractions the old-fashioned way, and I'd like you to know how to do it on your calculator. So if you did 225 divided by 180 on a TI calculator, you'll get a decimal. And then the math button, if you don't know this, I'd write a note about this. I probably showed this before. You go math, and then that option 1 converts it to a fraction, and it reduces it for you. So see, it's 5/4. That's a nice tool to know how to do on your graphing calculator. You can reduce fractions with it. Okay, so this next one is going to be 333 pi over 180. Okay, I always like, when this shows up when I teach, I'm always curious how many students know this. You guys know how you can look at a number and tell if it divides by 3 or 9?
Add them up.
Add them up, good. So 3 plus 3 plus 3 is 9. What does that tell you? That you can divide by 3 or 9. Okay, that trick only works for 3s and 9s, and it's sure it comes in handy. The digits there add up to 9, so both things divide by 9, don't they? Okay, so that's kind of, sometimes a lot of students don't seem like they've ever learned that, but it's good to learn those divisibility tricks. Now I'm going to do this just like in 2 steps. So if I take I'm going to do this with my calculator mostly here. So I got 333 divided by 9 is going to give me 37 pi. And then if I do 180 divided by 9, I get 20. And that's as far as you can go then. Okay, so that's typically one of the things you're going to do a lot. Real basic skill is be able to convert back and forth like that. Okay, all right. Now there's going to be times when you have no choice but to work a little bit with your calculator. So on these problems, we're going to work mostly with the calculator. So, and this one, I'm just going to have you round this like to the nearest tenth is what that says. Okay, you don't have a whole number. So what we're going to do with this is we're going to do the same thing. We're just going to do this totally on the calculator. So I do 185.5 times pi, and use your pi key, and then divide by 180. Okay, so you want to do that exactly like that, and if you round that off, that's going to give about 3.2 radians like that. Okay, now I made this problem up to see if the answer surprised you or not. I don't know. 3.2 radians, 180, is that logical? What did we say pi radians was? I said you could never forget it. Pi radians is 180, right? So if pi radians is 180, that's a tad bit bigger than pi, right? Well, so is 3.2, okay? So to me, a lot of times when you're learning this system, it's good to understand. You see something that's around 3 radians, that's around 180, isn't it? If it's 6 radians, it's around 360, you see what I mean? So that's good for estimation and so forth, okay? All right, the next one we do exactly the same thing. We do negative 345.95, just do the same thing on your calculator, multiply by pi over 180, and then round it off, okay? You don't have to put the negative in. All that means is it's a negative answer. So with this one, that's about negative 6.0, I'll round it to 1 decimal radian. See what I mean? That's like almost 1 lap around the circle. Actually, if pi is 3.14, then 2 pi is 6.28. So that makes perfectly good sense to me. You see what I'm saying? Okay, that's important. Okay, now we're going to do this backwards and kind of work with this a little bit. There's 2 ways to do this. If you're converting radians to degrees, you do that. Now, the only time that you're in degrees is if there's a degree symbol. Okay, if there's not a degree symbol, you're in radians. So if you go down to this where it says 3 radians, okay, there's no degree symbol, so that is radians, okay? So there's 2 ways to do this. One way to do this problem is to do the reverse of what I just did. The opposite of multiplying by pi over 180 is multiplying by 180 over pi. Okay, so we're going backwards. So if you want to do it this way, then the pi's would cross out, and then you can even reduce the fractions before you multiply if you want to. So 180 divided by 6 is 30. If you do it that way, you can do it in your head. So 5 times 30 is 150 degrees. So that's the first way you could do that. The other way, and this is the way I do it most of the time, is if I see a pi is 180 degrees, right? So just replace the pi with 180 and you'll get the same answer. That again divides out, so you get 150 degrees. So that's what I like to do, is just if I see a pi, replace it with 180 degrees, because that's the connection, okay? Same thing with this problem. You could either multiply by 180 over pi, cross that out, and again with this one, 180 over 3 looks like 60. Then you can take your calculator if the numbers get a little bit bigger. So 16 times 60 is going to be 960, so the answer would be negative 960, okay? So that's how you handle that, okay? Right, the next ones you have no choice pretty much other than to use your calculator. So if you're converting this to degrees, okay, what we're going to do is we're going to multiply this by 180 over pi, then we'll just round it on our calculator. Okay, so I'll go ahead and do that. 3 times 180, get the answer to that, and then divide by pi. And use your pi key and do all your rounding at the end. So when you're doing, My Math Lab, that's kind of how it's programmed to do. So that would be like 171.9 degrees, okay? Again, notice 3 radians, close to 180. That's the idea. Okay, next one you do the same thing. You do 9.5 times 180 over pi, and again, you use your calculator, okay? Okay, so I'll just round that off like to 1 decimal, so I get about 544.3 degrees is what that'd be. Yes?
For example 5, when we are converting each degree to measure radians, you said that 3.2 radians is about right because a radian is around 60 degrees, right?
No, not quite. There's a better way to think of this. Since pi is equal to 180, right, that would mean that 180 is close to 3.14. So what I'm saying is 3.2 is a little bigger than 3.14, therefore 185 is a little bigger than 180. That's better than what you're suggesting, but I know exactly what you're thinking is 60 degrees is a close estimate to 1 radian, but that's a little bit better way to look at it to me, okay? Okay, so let's do one more thing, and then we'll take a break on this right here. I'm going to talk about what coterminal angles are and kind of run through this idea. So what happens is, what a coterminal angle means is this. It just means if you have 2 angles and they have to be in standard position, if they have the same initial side, all that means is they start at the same point, they have the same terminal side, it just means they end at the same point. So this is a good example of this. So 120 degrees starts here and ends there. So does negative 240, right? And notice on this that if you took off that negative, 240 and 120 add up to 360, don't they? So coterminal angles just mean you start at the same place and you end at the same place. And there's an infinite number of coterminal angles. You could also do 120 plus 360, and if you did get that, you would get 480. 480 is also coterminal, because all that's going to mean is what? You take one lap around the circle, but you still end up at the same place, right? So what will happen is coterminal angles are always 360 degrees apart. Guys, just means more and more laps around the circle, either clockwise or counterclockwise. But they start at the same place and they end at the same place. So in degrees, two angles are coterminal if they vary by a multiple of 360. So in other words, you would have like this, 90 degrees, 450 degrees. What's after that? 45 and 36, what is that? That's what, 81, 810 degrees, and so forth like that. So they just get bigger by 360 and smaller by 360 infinitely. That's what we mean, okay? If they're in radians, well, what is 360 in radians? 2 pi. So they vary by 2 pi, okay? So what I'm going to do on this to go over this, I want to do these examples and then we'll take a break, is we're going to find what the directions of the problem say is find a positive angle that's either less than 360 if you're in degrees or 2 pi if you're in radians, and then we'll just draw a sketch of each one of these. So what you would do on this one is you would just take 415 and then you would subtract off 360 degrees. Okay, so if you did that, what is that, 55 I think? So that's 55 degrees. So you would have a 55 degree coterminal angle. Okay, if you do a sketch on this, because I want you to do a sketch on this just to kind of have a good idea what's going on. If you're in standard position, if you were to go through and graph 415 degrees, well, what would you do? First, you would go counterclockwise, and you would do one lap, right? And then what? Then 55 more, right? So that's how you graph 415 degrees, okay? If you did a second sketch, and you can just make a rough sketch on this, if you graphed 55 degrees, wouldn't it start at the same place and end at the same place? So therefore they're coterminal. That's why we call them coterminal, because they terminate at the same place. Okay, that's the idea. Okay, now if you were doing something like this, if you want to graph 17 pi over 5, to me it makes a lot of sense to change it to degrees, because then you'll understand better where you are. So what I'm going to do on this is pi is 180 degrees. I'm just going to take my calculator and I'm going to get what a degree measure is on this then, for the purpose of my graphing mostly. So I have 17 times 180, and then divide by 5. So that's going to give you 612 degrees. So that's what that converts to. Okay? So what I'm going to do on this now is I'm going to do two things. First thing I'm going to do is I'm going to sketch this 612, and I'm going to do this with the assistance of my calculator. So if I take 612, and then if I take away 360 from it, then what I'm going to end up having is I'm going to have 252, because we're trying to find a coterminal angle that's less than 360. So if you went through and plotted this, then you would start there, and then this would say it's a positive angle, so you would go counterclockwise, one lap, and then what? 252 more. So you count it out as you go. 90, 180, 252 doesn't quite make it to 270. So that would be how you graph 17 pi over 5, would be like that. Okay? So if you want this answer to be in radians, and I want to do this like this. If you want the answer to be in radians, notice that on this problem, I just subtracted 360. So if it's in radians, don't subtract 360, subtract what? 2 pi. 2 pi, good. Okay, so that way you don't have to convert it again. So when I find this coterminal angle, just subtract 2 pi over 1, get a common denominator, work it out that way. It's easier, it's less work. Okay, so that would end up giving you 17 pi over 5 minus 10 pi over 5. So that would end up giving you 7 pi over 5 like that. So that's your angle that's coterminal to it. And all that would end up being is it would just be this. It would just be you start here and you end there. That would be the 7 pi over 5 angle. Okay, does that make sense to you? Okay, right? Okay, now the next ones I'm not going to draw pictures on. I'm just going to get angles on this. So if you're going to do this, these are negative angles. So if it's a negative angle and you want to find an angle coterminal to it that's positive, what would you do? What's one lap in radians? 2 pi, right. Okay, so what you would do is you would add 2 pi over 1. Okay, just get a common denominator. So that common denominator is 7. So what you'd end up having is negative 31 pi over 7 plus 14 pi over 7, like that. Now this is going to give you a coterminal angle, but if you do that, you would end up getting negative 17 pi over 7, right? That's not a positive angle, so what would you do? Add 2 pi again. Yeah, just go another lap around the circle. So I'm going to go 2 pi over 1 again. It may still be negative. I think you have to do this several times on this one. So anyway, that would give you negative 17 pi over 7 plus 14 pi over 7. So that looks like that would give you negative 3 pi over 7, right? So what you need to do is just add 2 pi to it again. Okay? So by doing that, if you do that, you get a common denominator on that. It looks like what you're finally going to get is negative 3 pi over 7 plus 14 pi over 7. So it looks like that's going to give 11 pi over 7, like that. Okay, so that's one way to do that, is you just, and see what I see on this is this. If you did 31 divided by 7, that's what? That goes 4 times with something left over. So it's clearly more than one lap around the circle. So if you keep adding 2 pi, then eventually you'll get a positive answer. That's one way to look at it. Okay. Same thing with the next one. I'm just going to do this. So what we're going to do is add 360 to it. And we're probably going to have to do that a couple of times. You can do this totally on your calculator if you want to. So negative 760 plus 360, well, that's still negative. Okay, so add 360 to it again. That's still negative. That's what, negative 40. And then if you do negative 40 plus 360, that would give you 320 degrees. Okay, so the answer to this would be, if you were looking for a positive angle, then that would be 320 degrees. Okay, so coterminal angles are very simple. It's just they're off by 360, right? And they're off by 2 pi. That's what we mean. It's another more and more laps around the circle is what that means. Guys, everybody with me there? Okay, all right. So let's take a 10-minute break, and then when we come back, we'll finish this up, and then we'll get started a little bit into the trig functions and the unit circle tonight too. Visualize how radians go. And it has one other thing I wanted to show you on here. So basically, right now this is 1 radian. Why is it 1 radian? Because the radius and the arc are the same, okay? If I keep dragging this, it'll go like this now, okay? So now you've got 2 radians. What 2 radians means is this distance around the circle is twice as big as the radius, and so forth. If I go to 3 radians, okay, now I'm going to end up getting close to pi right there. So 3 radians is, we learned that all the way around the circle is pi. So notice 3 radians doesn't quite make it around like that. So this is saying that the distance from here to here is 3 times bigger than the radius, and so forth. If you make it all the way around the circle, you start getting into 2 pi radians, so it's like almost 6 trips around like that. Does that make sense to everybody? A lot of times students don't understand what radians are. They know how to convert, but they have no idea what it is. And the other thing I wanted to show you is it doesn't matter what the circle is. If you make the radius, if you change the radius, that radian measure ratio still stays the same. Does that make sense? Okay, so I wanted to show you that real quick. And then the next thing I want to look at is the idea of this arc length formula, and talk about this a little bit and where this formula comes from. So what I want to look at in here is we have the arc length formula, S equals r theta. S is the length of that arc, r is the radius of the circle, and then theta is the central angle. But what you have to pay attention to is, if you were in degrees, you would get a ridiculous answer. Okay, I want to show you kind of what I mean by that. So like, for instance, if you had a circle and say that this was a 20-degree angle, and say the radius was 2 inches, okay, or something like that, then according to this, S is equal to r theta. If you do S equals r theta, you would have 2 inches times 20 degrees, so you would get 40 inches, okay? Now you tell me, don't you think that's a tad bit big? If that's only 2 inches, then you're telling me that distance is 40? And I see students do that all the time on this, so you got to make sense of your answers. There's no way in the world that's 40. So the way that you have to do this problem, so you have to do this. You have to change that 20 degrees to radians by multiplying by pi over 180. Now I'm just going to do it on my calculator, just more or less to demonstrate this to you. I'll just get a decimal. So if I go 20 times pi over 180, then I'm going to get this, okay? Then if I multiply that by 2, see, that would be the radian measure of 20 degrees. If I multiply that by 2, then I'm getting about 0.6, okay? What do you think of that? That's 2, that's 0.6, isn't that a tad bit better? You see what I mean? Okay, because I see that all the time. Students don't pay any attention to the degree measure and they get just totally nonsense answers. So when you're doing this, it's real important that you are in radians. This formula doesn't work unless you're in radians. Okay, so I'm going to show you where this comes from and kind of give you this idea. The derivation of this formula is very simple. The idea is if you look at a circle, you're going to relate the small part. This is kind of a part to a whole proportion. So you're going to do this. What I'm going to do on this is I'm going to relate these parts of a circle. The arc length is a piece of a circle, right? The circumference is what? All the way around. So you're doing the part to the whole. The central angle is the angle inside. What's 2 pi? That's all the way around the circle. 2 pi radians is all the way around the circle. So here's where the formula comes from. So the arc length, replace the arc length with S. Change that to S. What was the formula for circumference of a circle? 2 pi r, okay? Pi r squared is area, you have that. The central angle we'll call theta, then we'll put a 2 pi like that, okay? So I'm doing the arc length compared to the circumference, the small angle compared to all the way around. Now I cross multiply, and I'd have S times 2 pi is equal to 2 pi r theta. If I divide both sides by 2 pi, well, that's where the formula is. It comes right out of that. So S is equal to r theta. Okay, does that make sense? Okay, is that logical? Okay, all right, that's where it comes from. It's always good to know where some of this stuff comes from. It doesn't just fall out of the sky. Somebody's got to figure it out. Okay, so we're going to do just 2 problems with this. So if you're doing the arc length on this, what we're doing is we're finding the length of this arc right here. So that's what S is. So we're going to use S equals r theta. What do you have to do with theta first? Or to radians, otherwise it's nonsense, okay? So the way we change theta to radians is we multiply by pi over 180. Now we're going to get an exact answer and a decimal answer. So if you cross out the zeros, you would have 10 pi over 18. Then if you divide the top and bottom by 2, you're going to get 5 pi over 9. So you've got 5 pi over 9 radians is what you have. Okay, so that means take the radius, which is 3, and it's 3 units. It doesn't matter if it's inches, feet, or whatever. Now multiply that pi over 9, and then you would get 15 pi over 9, and then that could reduce by 3, giving you 5 pi over 3. Okay, so that's the exact length of that arc, but I'm going to take my calculator because I want to see if this makes sense to us or not. So if I was to take 5 times pi and then divide that by 3, then I end up getting that S is approximately 5.2 units, okay? What do you think of that? This is 3. That's 5.2. That seems pretty logical to me. How about you? Okay, because if you didn't do that, if you did 3 times 100, that would be 300. You see my point I'm trying to make? Okay, so when you get an answer to stuff, man, you want to think about it. Okay, that's important. Okay, so here's one thing this is kind of a basic example on this. So a way to approximate the distance between 2 cities using this formula is by looking at this. So this is basically saying that you have 2 cities. Okay, here this is, I think, Glasgow in Montana. And then this is Albuquerque. It's not really drawn to scale very good, but you have that. Okay, I'm giving you that the radius of the Earth is approximately 4,000 miles. So the thing is, on this, if these cities are straight north of each other, they have to be straight north of each other, or the mathematics gets off a little bit, then you have to get into what's called spherical trigonometry. Well, what we can do is just figure out what that angle is based on the longitude, or the latitude, I'm sorry, then you can use that formula. So what we would have on this city is 48.15 degrees north. That just means the equator, 48-degree angle. Albuquerque is 35.8, and I took these off of a map so they're accurate and everything. So you have that. So what you would do if you wanted to find theta, what would you do with those two angles? You'd subtract them. You'd find how far apart they are, right? Okay, so we'd do 48.15 degrees and then minus 35.08 degrees. So you want to do that first. I'll just take my calculator and do that. So 48.15 and then minus 35.08. Okay, and that'll give me my central angle. So theta is about 13.07 degrees, right? Okay, now what do? You change it to radians. Okay, so theta, you're going to take 13.07. You're going to multiply that by pi over 180. And again, we'll just do that totally on our calculator. So I'm going to take that multiplied by pi and then divide by 180. Then I'll use several decimals on that. So that angle is about 0.2281 radians, like that. Okay. Now what you want to do is, next thing you do is you do S is equal to R theta. Okay. So what you do is take the radius of the Earth. This is approximate. I think it's more like 3,900 and something. So it would be 4,000 miles, and then multiply that by the radian measure, and then you would get a sensible answer. I tried to pull this off of a map so I'll get a sensible answer on this. I don't have any idea how far apart that is. It's probably 1,000 miles or something like that. I don't know. So let's see, 4,000 times 0.2281 is about 912 miles. Okay, so and those two cities are pretty much directly north of each other, I think. So you could use that formula. But if they weren't, you couldn't do that. Like if you were to find the distance from like Denver to someplace in Florida, you couldn't do this formula. You have to do what's called spherical trigonometry. So this is kind of limited to things directly above each other. Okay? Okay, so that's how that formula goes. The other basic thing I want to look at here to kind of finish up angles here is degrees, minutes, and seconds. Okay, so we do this from time to time as we have a way to look at decimal parts of angles. Okay, so the idea on this is if you have like this is 30 degrees, but 30 degrees could be chopped up into little pieces, and every time you have 1 degree, then you can use minutes on this. So the idea is if you have 1 degree, that's 60 minutes. You want to know what the basic conversion factor is on that. So every time you have a degree, you can chop it up, further subdivide it into 60 minutes. And then if you have 1 minute, then that's 60 seconds, just the same way it is in time, but where this is a way that we measure angles. So what would happen is 1 degree would be 60 times 60, or 3,600 seconds, like that. So those are the basic things on that. So a second is just a tiny, tiny fractional part of a degree. So it kind of turns out that you have this, that basically one minute is equal to 1/60th of a degree. Okay, so it's a fractional part. And then 1 second is equal to 1/3600th of a degree. So you're just doing fractional parts like that. So I want to show you how you do conversions, because you'll need to do this from time to time. You totally use your calculator on this. So I'm going to show you a couple of ways to do this. So the first thing that you would do, whenever you see this symbol, that's minutes. If you have 1 tick mark, then if you have 2 tick marks, that's seconds. So this is saying 256 degrees, 36 minutes, 24 seconds. So what you want to do is, this is what you want to write on your paper. You're going to do 256 plus 36 out of 60, because there's 60 minutes in a degree. So that's really giving you 256 degrees plus 36/60ths of another degree, and then you do 24, not 60, but 24 3600ths. So what you're doing is, that's a fractional part of a degree because it's minutes. That's a fractional part because it's seconds. Now, from here, you do your calculator. I wouldn't expect you to do this in 2018 any other way. So just get your calculator out and just do it in one step. So I'll go 256 plus 36 over 60, and then finally plus 24 over 3,600 like that. Okay, and then we'll just round that off, and that'll change this to a decimal. So this is approximately 256. Let's just use like 2 decimals. I'll round that off to 256.61 degrees. Okay, so let me ask you something about this too, because this is again something you want to have an estimation technique in your head on. Okay, if 60 minutes make 1 degree, then what would half a degree be? 30, right? So half a degree is 30. Well, half is 0.5, right? So 0.6 is a little more than half, so it's 36. You see what I mean? Okay, so you want to use that estimation technique. 0.5 should go directly to 30. So that's kind of how you learn how to estimate these things. Okay, the next one. This one you need to make like a strong note on this one. Students mess up on this all the time because of the negative. So put beware or something. Okay, I'm not kidding. What you do is you do that on your calculator. You do this. You can go like negative parentheses, or you can just not even put the parentheses in. What you don't want to do is just put the negative in without parentheses, or it will not do what it's supposed to do. So we just do 54 plus 12 over 60, and then plus 38 over 3,600. Okay, now I want to show you what happens with this on the calculator. The way that I do this is like this. I just go, well, let me do it this way first of all. So I'm just going to go negative parenthesis 54 plus 12 over 60, and then plus 38 over 3,600. And then I'll close the parenthesis like this. This is one way to do it. It's just like that. I don't do that. I just forget the negative, do the conversion. I just know the answer is negative. Okay. But what I see students do all the time is this. Negative 54 plus 12 over 60. I just want to show you what happens if you do this and why. So if I was to go through and put this in like this, notice that it gives a totally different answer. Okay. And it gives the wrong answer. Because see, what you want this thing to do is you want it to do this. All that means is it's negative. That just means you're clockwise. That's all it means. So either do it this way or just do it the way I do. Just put that in and then just have a negative answer. You see what I mean? Okay, so that's real important that you pay attention to that. So the answer on this would just be negative 53 point, and let's say negative 53.79 degrees like that. Oh, that's the wrong one. I was trying to make such a big point of that, wasn't I? Okay, thank you. Negative 54.21 degrees is what you should have. Okay? All right. Now, let me show you a second way. To me, that's the way to do it on a TI. You can also, if you got your calculator, you might want to look at this. On all of these TIs, usually above the apps button, try to find your apps button, which is in the second column. You should see the word angle above that in blue or some other color. So if you go second apps, then you'll have an angle menu. So that's where your degree symbol is, and this is where your minute symbol is. Okay, and I don't know if anybody you has the second symbol on there or not. I don't. The most common place is the second symbol is right above the plus in green. That's the way it is on my calculator. And that's the way it is on most calculators. Why they did that, I have no idea. So you could do this problem this way. Okay, and just try this with me if you want to, but you don't have to do it this way. So let's take, like, for instance, this first problem we did. You could go 256, then you could go second apps to get the angle command to come up, press enter, and then the degree symbol comes up. Then 36, you put in the 36. That's not what I wanted to do. Why did it do that? Okay, so I go on 36, and then I go again second apps. Okay, then you go down to the second option and put that in. So the minute comes out. Then you can put in 24. And then you got to go alpha. On mine, it's color-coded, so it's alpha plus. Then that comes out. And it gives the answer. Okay, I don't do it that way because it takes too much time to find everything. So in my opinion, I would just do it the first way, but I don't care. You just need to know how to do that with your calculator, and you're always going to do these kind of problems with your calculator. Okay, everybody with me okay there? Okay, all right, so you want to know how to do that. You also want to know how to do that backwards. And the thing with this is now we're going from a decimal to a degrees, minutes, and seconds. So what you do on this is, first of all, the 120 degrees, that's set. What you do is take the decimal part and you multiply it by 60. A minute ago we divided by 60, so we're undoing and going backwards. So that gives 36. So that would just be 120 degrees, 36 minutes, which makes perfectly good sense to me. I hope it does to you. Remember, 30 minutes is 0.5, right? That's 0.6, so it makes sense to me that it's a tad bit bigger than 30. What do you think? Okay, get that down, because that's how you catch mistakes. I do that all the time. Okay, the next one you would do the same thing on. Again, you would just have negative 405 degrees. Then you want to take 0.37 times 60 on your calculator. And let me show you a little bit different thing happens on this. So what you can do with this is you do the 0.37, you multiply it by 60, and that's going to end up giving you 22.2. So you want to take the 22 and put minutes there. But you have a leftover decimal, so what you do with that is you take the 0.2 and multiply that by 60. So if you do that, you're going to get 12, so that's 12 seconds. Okay, so that's the idea with that is take the decimal. See, on this one, when I did the decimal times 60, it just turned out to be a whole number. So I'm done. Over here, I have 22.2, so you want to bring that over to the seconds like that. Okay, everybody okay with that? Okay. Now, let me show you how you can do this on the calculator. It's actually very easy to do this on the calculator. So if you took like the problem we just did, you could do this. Okay, I'm going to type in negative 405, 0.37, and then I'm going to go again second app, and then there will be a command, and write a note of this if you need to. It's just DMS. That stands for converting to degrees, minutes, and seconds. Press enter again, and it comes out, and the symbols come out. So you can do that way if you want to. Okay, I like using that one because that's pretty simple to do because everything comes out automatically for you. Okay, all right. So that would be the ways that you're going to do that. Now the next problems you're not going to use your calculator on. Okay, what would 120.5 degrees be if you changed it to degrees, minutes, and seconds? 120 degrees, 30 minutes. How about the next one? What's half of 30? 0.25 is half of 0.5, so what would this be? 120 degrees, 15 minutes. How about 0.75? 45, good. Okay, that would be 120 degrees, 45 minutes. Okay, that's for estimation. To me, a student ought to be able to immediately tell what those things are. Anything else, get your calculator out. Okay, that's my idea. Okay, so one last thing we look at in this section, and we do this pretty briefly in pre-calc. Some of you had Trig from me, and we do a lot more work with this in a Trig class, but we look through the idea of linear and angular velocity just as a physics application of angles, because it's good. If you're going to get into engineering and physics and stuff like this, it's good at this level to start seeing a few things come up. Okay, so what angular velocity is it's defined by this equation right here. A couple of things that you want to make sure that you understand is omega is the variable. That's omega is what we use to represent angular velocity. Okay, and what everything else means in this formula is you've got alpha is a central angle, so that's just an angle in radians, and then t is time. Okay, so what you end up getting when you're doing angular velocity, the units typically are this way. They're usually radians per unit of time. So it could be like radians per minute, radians per second, or something like that. Another possibility is like RPMs, which stands for revolutions per minute. Okay, that's a real standard that we use to measure this. Okay, so if you're looking at angular velocity, one of the best ways to do this is next time you get in your car, look at your tachometer, because that is measuring angular velocity. So what that's saying, okay, you get in your car, this is measuring not how fast you're going in miles per hour, it's telling how fast your engine's cranking. So what it's doing is it's telling you how many revolutions that your engine is going in a unit of time. So if you were up there, that would be 4,000 times the engine cranks in one minute. And it goes up, it goes to the next gear, and so forth like that. So think of that as measuring how many rounds that goes in a minute. So what it's really doing is it's measuring an angle that it's traveling through in a unit of time. Okay, does that make sense to you? Okay, so that's different than linear velocity. Okay, so you might say like a fan rotates at 1,000 revolutions per minute. Now I do want you to write this down because you're going to need to do this from time to time when you're working with this. So if you wanted to convert this to radians per second, I want to just do a conversion here, because a lot of times when you're working with these problems, you got to convert revolutions to minutes, radians, and so forth like that. So it goes like this. Okay, if you want to get rid of revolutions, then of course you put revolutions there so it'll go away. And you want to end up with radians. Okay, we call this a unit fraction. Okay, now we learned this tonight. What is 1 revolution in radians? 2 pi, good. Okay, so that's 2 pi radians. So that would take you, that's how you convert revolutions to radians. Okay, you already know hopefully how to take minutes to seconds. So again, you want minutes to cross out, so you put it in the top. You want seconds in the bottom, and then the conversion factor is 1 minute, gives you 60 seconds. Okay, so if you went through and did this and multiplied straight across, you would have 2,000 pi radians over 60 seconds. Then you could take your calculator, and I'm not going to do that, but you could take your calculator and just round that off to something, okay? So you want to make sure that you understand that 1 revolutions goes with 2 pi radians. That's the conversion factor you're going to use, okay? Okay, let me talk a little bit. I'm going to do a couple of problems, and we'll kind of do some linear velocity and kind of wrap this up. Okay, these problems right here, what you're doing is we want to start with kind of understanding of what the terminology means in here. So this says an engine has an angular velocity, 2,400 revolutions per minute. All we're doing on this is we're just doing a unit conversion. Okay, so let's do that real quick, just like the last problem, and then we'll go ahead and get the calculator and get an answer on this. Okay, so we're going to take that and we're going to change that to radians per minute. Okay, so if you want revolutions to go away, you put it in the bottom. You want radians to end up on the top. Again, what you have is 1 revolution goes with 2 pi radians, like that. Okay, if you've taken chemistry, physics, and stuff like this, we call this dimensional analysis. That's how you convert units. Okay, and then the next thing we want is, we've already got minutes, so we're good. So what we would have is 4,800 pi, and then we'll just write radians per minute. I'm not going to take a decimal, but you could. Okay, that's what you would do. Okay, let's do one more conversion on this, just kind of backwards. So this one is saying you have 900 radians per second. So what we're going to do on this is we're going to change this to revolutions per second now. Okay, all right, so if you want radians to go away, where do radians go, top or bottom? Bottom. You want to end up with revolutions, so that's on top. Okay, where does the pi get? Where does the 2 pi go, and where does the 1 go? 1 revolution, 2 pi radians. Okay, so it's different this time. It's backwards. Okay, so that would end up putting you in revolutions per second. So that would end up giving you 900 over 2 pi revolutions per second. And then I'm just going to take my calculator on this, just do a decimal. Now, if you do the decimal on this, you got to do 900 divided by 2 pi, and notice that I'm doing that 2 pi, or trying to do it anyway, in a set of parentheses. So you'd have to go 900 divided by 2 pi, like that, and that's how that would end up. So you'd have about 143.2 revolutions per second. Okay, so that's a fundamental thing when you're working with this, is just know how to convert units around. Okay. Okay, now let me talk a little bit about what linear velocity is. Okay, well, next time you're in your car, like tonight maybe, okay, you have a speedometer which measures linear velocity. And what it's really representing is it's really doing this. If you ever wondered how your speedometer is working, it's really measuring the distance that the edge of your tire goes in a unit of time. So that's what this is doing. It's doing the arc length, which is a little piece of your tire over a unit of time. Okay, so that's actually what's going on, is it's measuring that distance. So what we have in this formula is V is linear velocity, S is arc length, time, and then the basic units on this is what you're familiar with, miles per hour, meters per second, that kind of thing. Okay, so that's the idea. Okay, the formula that I want to talk with here to kind of wrap this up is there's a connection between the two. Okay, so if you have this formula V equals R omega, of course that's your linear velocity, so that would be something like miles per hour or something like that. This of course is your radius. Okay, then omega is your angular velocity, like that. So they are connected, and you're going to use this formula a lot of times when you're solving problems involved in this. Okay, so let me show you where this formula comes from, and then I'll finish this section up with just a couple of examples. So with this one, I want to prove this formula. Okay, I'll show you how this is proved. And it's actually a real simple proof. Okay, what we're going to start with is we're going to start with this formula right here. We're going to start with the formula V is equal to S over T. So you want to write that down. Remember, that means arc length over a unit of time. Okay, now what we learned today was S is equal to R theta, right? Okay, we got that. So replace S with R theta and leave the T alone. Okay, so what happens is you got to understand what this is. Theta over T, we also learned just about like a few minutes ago, that's omega. Because what omega is it's the angle something travels in a unit of time. So what you would do is change that theta over T to omega, and then you got it. V is equal to R omega. So that's where that comes from. That's the derivation of that, okay? So to me, one of the things that's real key when you're learning this is to understand conceptually what the difference between the two is. So an angular velocity, what does that measure? It measures how many times you go in a circle in a unit of time. So that's basically just doing like an angle that you're going through in a unit of time. Or think of it as revolutions in a unit of time. Think of the tachometer. Linear velocity is a distance over a time. So they're totally different things, okay? All right? So let's work out these last two examples here, and then that'll finish up this section, and then we're going to lightly kind of talk about unit circle in 4.2 tonight. We'll just kind of get started on that. Okay? So this problem says you have a wheel that's rotating at this. Now here's the thing here's why students have trouble with these problems. You have to immediately know what I gave you. And you know based on the units. Radians per unit of time. Which is that? Is that angular velocity or linear velocity? Angular, okay? If it was meters per second, what would it be? Linear, okay? That's the whole key to solving these problems, is you've got to know what the units are telling you. So what this is that's omega. Omega is the letter we use to represent angular velocity. So I'm just going to write that down as omega is 3 radians per second. Okay, then I got a diameter. Okay, so the diameter of the circle is 80 inches. Okay, then what we're supposed to do is we're supposed to find the linear velocity. So we're going to find the linear velocity in feet per minute. Okay, so here's the thing on this. Okay, the formula that I just taught you was V equals R omega. So if you look at this particular problem, you already know omega, right? You don't know the radius, but it sure is pretty easy to find because I gave you the diameter, right? So what's the radius? 40, exactly. Remember, a radius is half of the diameter, so that would mean your radius on this is going to be 40 inches, okay? So when you put this together, you're going to do this. You'll take the radius, which is 40 inches, and then you're going to multiply that by the angular velocity, which is 3 radians per second, like that. Okay, now we got to change this to the right units. You're supposed to put this in feet per minute. Okay, so one of the things I want to explain on this a little bit is basically this. So if we're going to take this into feet per minute, we need to basically do two conversions. The other thing I want to explain is this. radians is not really technically a measurement. It is a placeholder. It's a name for that angle. It's not technically any kind of a unit, so you can just ignore that and just pretend like it's not there. Because you're not going to end up with radian feet per second. That doesn't make any sense. Okay? Radians is a placeholder. So I'm just going to kind of ignore that and kind of scratch that out. The rest of the problem is just doing conversions. So we want to take inches to foot. So we would go like this. Put inches in the bottom so it cancels, feet on the top, and then the connection between that is there's 12 inches in 1 foot. Okay, so make things cancel the right way. You also want seconds to be converted. So if seconds is in bottom and you want it to cancel, you put it on top, so it will. And then you end up with minutes in the bottom like that. Then the conversion factor there is 60 seconds, make up 1 minute like that. Then the rest of the problem you do on your calculator, and then you got it. So you can pretty well do this in 1 step on your calculator. Okay, so what I'd end up having from here is I'd just go straight across. So I'm going to go 40 times 3 times 60, and I'm going to record that. So that's going to give 7,200. Oops, 7,200. Then the bottom you have 12. So if I take that divided by 12, that will give me, what we get is 600. And now we are in feet per minute. So most of that problem was a unit conversion problem. So you would get feet per minute like that. Okay? Now that problem's not that hard to do, but the reason students don't do well on this is because they don't understand what they're given. Okay, that's what the whole key to me in learning these problems is to know what you're given based on the units. Okay? Okay, so let's do one other one like this because we kind of lightly cover this in pre-calc. So this is basically saying you have a pulley of radius 7. I just start writing things down and getting the variables down. That's 7 centimeters. Okay, now here's the key. It rotates 15 times in 128 seconds. I just gave you something. Did I give you an angular velocity or did I give you a linear velocity? It's angular, because anytime it's telling you how many times you rotate in a unit of time, that's an angular velocity. And what is the letter for angular velocity? Omega. So what we write down is you write down omega equals 15, and it's implying that it's 15 revolutions in 128 seconds. Okay, like that. Now the question said find the angular velocity. It's already there. Okay, so basically what you would have is you would have this answer right here. Now you could change this to something if you wanted to. So you would just basically, if you did this like on a calculator, you would have 15 divided by 128. And then that would give you like 0.1171875 revolutions per second. Now the problem doesn't say anything about what units it should be in. But again, the point behind that is you were already given it. Okay, right? Now that's about the extent we're going to do with this. On your homework, I didn't put much on my math lab on this, other than just very basic things because of the time factor. Okay. Okay, so let me